functions like smoothing, but also to sort of find strong responses just like the templates. And we'll do that actually in the next couple of lessons. Welcome back to Computer Vision. The last lesson we started talking about filtering as a way of finding a specific pattern in an image. We talked about template finding. And the idea was that given some pattern, correlation or convolution would be some way of finding that pattern in the image. And we assumed that the goal thing that we were looking for was given to us. And then there was also this idea that, well, maybe we could just take the locations where this pattern was found, and that became sort of a description of what we were looking for. You could even think of that as describing the image, although we didn't talk too much about that. But again, that's the idea that you know what the important thing is that you're looking at. But what about generic images, ones that you don't know in advance what's going to be in the picture? What are some good, the word we sometimes use, features, what are some good things to try to find in the picture that might capture a lot of the information there and sort of give you the essence of what you need to work on? So to get some insight into this question, I want to show you some very greatly reduced images, which are still going to be meaningful, that is, you know what's going on to me and you. So normally when I do this in class, what I do is I say, raise your hand when you can tell me, if you can tell me what's in the picture. So I would show them this, and everybody would raise their hand and they would say it's some goofy looking lion. All right? And I would show them a picture like this. Okay, there's an elephant. There's a really cool old car. There is something I'm never going to own, a private jet. But what you can see about these pictures is there's actually not a lot of pixels being used in these pictures of different grayscale values. Instead, somebody's just sort of drawn in the edges, and yet that conveys to you a lot of the information. So the idea is that, in some sense, edges in an image seem to be important. They seem to convey something about what's going on. Let's talk about edges in just a generic image, and how it is that edges come to be within a picture. So what you can see here is, this is some ancient picture somebody drew out, that there are edges that happen for a variety of reasons, right? So here's one right there, okay, and that's at a depth discontinuity. First we're looking at the bottle, then we're looking at the background. Here's a shadow edge. Of course, shadows aren't really that harsh, but go with me for there. There's the idea that there's a discontinuity in the illumination. Up here, from this top to there, there's a discontinuity in the surface normal. That is, the shape is one way, and then the shape changes and it's pointing in a different direction. And then finally, edges here can be to essentially color discontinuity. So we go from white to black on the same surface, same illumination, same shape and everything, but the reflectance is actually different. So that's what edges look like. We can look at them in a real picture. I think this is UT Texas, which would mean that, again, this was stolen from Christopher Grumman as well, borrowed. All right. So in a real image, we have depth discontinuity, so the side of the building. We have shadows, so there you can see the shadow being cast by the sun on the front. What's interesting is we have texture, so if you were to blow up this area, and maybe we'll take a look at some texture later, just from the texture, or you can think of it as paint, things that are on the surface, you get different edges that show up. And then finally, the top ridge of that little cement thing, the edge around the ridge on top, that's like the top of the bottle cap. Same stuff, same color, but I get a discontinuity in surface orientation. So our goal for today, and next time also, is to find the edges in an image. Or to put this another way, we want to convert an image, which is a function of x, y, into a reduced set of pixels or curves, etc., that are the important elements of the picture somehow. And the idea is that it encodes the changes that matter to you. So here's a simple question. Edges seem to occur at change boundaries that are related to the shape or the illumination, which is not such a boundary. An occlusion between two people, so I'm here and somebody else is there, and there's an occlusion between me. A cast shadow on the sidewalk, a crease in a piece of paper, or a stripe on a sign. Well, as we said before in the picture of that bottle, this last one, a stripe on a sign, that's not actually due to a change in any of the physics of the shape or the illumination. It's actually due to a change in the reflectance function. Okay, and we'll talk about that later when we talk about reflectance functions. But the idea is that it's not part of the nature of the geometry of the shape of the object or of the scene, but of having to do with the reflected texture or reflected color. So the question becomes, what do we do, how do we compute to figure out that a pixel in an image, the pixel at some location x, y, is actually an edge pixel? That is, that it lands on an edge or is part of an edge somehow. To think about this, we have to return to our idea of an image as function. So you remember, here's our comedian, and this was two different representations of the same function. One just happens to be shown to you as a picture, so you're used to seeing that, although it's pretty scary. And the other is shown as this height map, where the height was proportional to the intensity. And the thing that's clear is that these edges, right, so this edge by the side of her face there, is really a steep cliff by the side in that function, okay? And what we're going to look for fundamentally for edges are going to be these steep changes somewhere in that image function. So it sounds pretty simple, okay? In some little local neighborhood, can I determine that I'm at a location where there's going to be a very strong change? Doesn't seem so hard. Well, there are two things that we have to sort of answer in order to be able to do this. If we're trying to look at a neighborhood with strong signs of change, we have this question of, well, how big is a neighborhood? And then, what do you mean detecting change? How much of change is change? And how are we going to determine exactly where that change is? So here's an example of a function, and the idea is that, probably the edge might be thought of as like that. Our first problem, of course, is we don't get to do that. We have to pick the pixels that we say are the edge, right? We don't get to say it's between, well, we could say it's between pixels, but we tend not to do that, right? So the idea here is that the 80s are on one side and these 20s and 30s are on another side. So we have to try to go about finding those. Change is going to be about what when we talk about functions? Well, change is going to be about derivatives, all right? And this is why we're going to be able to talk about derivatives with respect to our functions. So here we have a very simple image. And I'm going to show you a plot here of a horizontal row. So if we just take a row and we were just plot it, you'd see it starts out high, and then it comes down smoothly, and then it goes back up again. All right, so this is a nice, smooth image. Well, as you remember, when you were taking a look at change back in calculus class, you would take the derivative. If I apply the derivative to that function, I would get a function that looks like this. So this is the first derivative of that scan line. And these edges, which are these edges, correspond to these extrema of the derivative. That is, here's somewhere down here is where the maximum negative slope is, and somewhere over here is where the maximum positive slope. This is the maximum negative, that's the maximum positive. So finding edges is going to have something to do with finding peaks in the derivative. So how are we going to find these extrema in the derivatives? Well, the same way we found other things, right? How did we find Waldo? We ran some filter, we applied some filter and looked for its response. So we're going to filter our image with the appropriate, the word is operator, in order to find these peaks in the derivatives. So let's talk about differential operators. Okay, so a differential operator, when applied to an image, it returns some derivative. Okay, and we're going to model these operators as filters, as masks, as kernels that are going to compute that image gradient function. All right, and then we're going to threshold this gradient function to select the edge pixels. All of which brings us to the question, what is a gradient? All right, so here you got to go way back in your mind there somewhere for those of you, and I guess I make too little. I mean, many of you are heavily involved in the getting your degree or your courses, and you've been taking all these math courses. If so, I apologize for being so pedantic. For those of you who haven't looked at a calculus course in a while, we're going to have to remind you a little bit about multivariate calculus. Okay, and multivariate is when you had a function that was a function of more than one variable. So, for example, an image is a function f or I of two variables, x and y. And when I have functions that are a function of more than one variable, I can take what's referred to as a partial derivative, the derivative in the x direction or the derivative in the y direction. And the gradient is the vector that's made up of those derivatives. So let's take a look at this for images. So I'm going to write this as the gradient of an image, and this is that operator that I'm going to use to show the gradient. In an image, it's just a two vector made up of the partial of f with respect to x, the gradient of the image in the x direction, and the partial of f with respect to y. Okay? So here's an image, and as you can see in this image, it's only changing in the x direction. So its gradient would be whatever the change is in the x direction and 0 in the y direction. Likewise, here's an image that only changes in the y direction. Now, in this case, I'm talking about I was drawing the arrow in this way, we can either think of y as going more positive as you go down, we talked about this, or you can just say that this is the direction of the gradient in the sense that in this direction is where it's getting brighter. Okay, so in this image, my gradient would be 0 partial of f with respect to x, but I would have partial of f with respect to y. And normally, of course, I have change in both direction, and that's the gradient itself. It's the partial of f with respect to x and the partial of f with respect to the y. And it has both a magnitude, how quickly things are getting brighter, and also you can see there's this angle, which is sort of the direction of that gradient. And the gradient of a function is the direction of most rapid increase in intensity, and the magnitude of that vector is how much it's changing as a function of a unit step in that direction. Here we're just expressing all of this mathematically. The gradient is given by the two partials. The direction can be computed by just computing the arctangent. That is, the arctangent of the change in y over the change in x. Computer people amongst you should probably use a tan 2, so that if the partial of f with respect to x is 0, that your machine doesn't explode. And then we can also talk about the magnitude of the gradient, which is just the magnitude of these sum, and that's telling you how rapidly the function is changing, which of course is clearly going to be related to something to do with edges, because remember we said at edges we get steep cliffs where things change tremendously. So we're going to look for large magnitudes of gradients when we're finding edges. So, quick quiz. What does it mean when the magnitude of the image gradient is 0? The image is constant over the entire neighborhood. B, the underlying function is at a maximum. C, the underlying function is at a minimum. And D, either A, B, or C. It's A, B, or C. If you remember from calculus, right, when you have a function, when it gets to the maximum, it's neither going up nor down right there, right? So the gradient, the slope, is 0. So I have a function, so I have an image that's got a nice bright spot, and I'm at the spot that's the brightest, right, the gradient is going to be 0. Likewise, if I'm in a hole and I'm at the part that's darkest, the gradient is going to be 0. And of course, if the entire image is 118, okay, constant, there's no change anywhere, or just over a neighborhood, also the gradient would be 0. So the gradient is 0 in any of these three cases. So look, so what we were just talking about is fine for calculus class where you got all those fancy little Greek symbols, and you probably by now wish you were paying a little more attention to those Greek symbols. But the question is, how do we do these things in a computer where we don't get to do continuous math? So to do that, we have to talk about discrete gradients. So in continuous math land, the partial of f with respect to x is just this limit, right? So we move a little bit in the x direction, epsilon, subtract off the original one and divide by epsilon. And when we let that limit go to 0, that becomes our derivative. But in discrete world, we can't move arbitrarily close. We have to take what are called finite differences. So what we're going to do is we're going to talk about approximating our partial by some finite difference. So the simplest finite difference is this one, right? I take one step in the x direction, and I see what the value of the function is, and I subtract off the original, and I divide. How big was the step? Just 1, so that just becomes this value. So we say it's approximately f of x plus 1 minus f of x, okay? And that's called the right derivative. You get it? Because it takes step 1 to the right. Oh, wait. 1 to the right. Yeah, right, left, for those of you who aren't looking at this thing in a mirror, okay? In order to talk about the right way to think about these derivatives, let's take a look at our finite differences a little bit more. So here we have a picture of the striped duck that David puts in his book very often, David Forsythe. And you can see here we have this, it's a zebra, okay? So we have this picture of the zebra, which has all these stripes on it. And over here we have one of those finite difference images. First question, is this the finite difference in x or in y? Well, let's take a look. Here I have these nice kind of almost vertical stripes, and as I go across, you can see that I get a bright value and a dark value and a bright value and a dark value. So in other words, as I'm seeing changes going horizontally in x, I'm getting different values of whatever this finite difference is. But across here, I have hardly any changes in x and only changes in y, and you'll notice this is not a very strong signal there. Okay, so this is going to be a finite difference in x. One of the things that might be bugging you about this is on the right-hand side here, I'm showing you an image that has positive numbers and negative numbers in it. So here's the deal. Normally when we display an image, we make 0 black and some other number white, or we